All right, hello. This video is going to talk about conservation laws in electricity and magnetism, roughly corresponding to chapter 8 in the textbook and lecture 18, sort of going in parallel with lecture 18 and an introduction to lecture 19. So first, remember from electrostatics that we could compute the energy, the electrostatic potential energy, by integrating over this quantity, epsilon naught over 2 e squared, that we call the energy density of the electric field. There were other ways to calculate the energy, but this one was nice because it sort of told us that the energy was located wherever there was field, and there was no energy where there wasn't field. And that's ambiguous in electricity and magnetism. We can't really say where the energy is most of the time. This is one way of calculating it. And something that we glossed over, but is in the textbook in chapter 5, is how to calculate the magnetic energy in a magnetostatic system. And it's exactly what you would guess. It's 1 over 2 mu naught b squared is the energy density, energy per unit volume. And you integrate that over the volume to get the magnetic energy. And that follows either just by guessing the analogy, or you can think about inductors and integrating the EMF around an inductor to find the work done in setting up a current, for example. But both of those formulas only hold in static cases. And so we want to figure out, how do we talk about energy in a field when the field might be changing in time, and so the energy might be changing in time, and that's related to work. And how do we keep track of all that? So what we're going to do is we're going to start with the work, and the work is just the force dot dl. This is an infinitesimal amount of work dw. I plug in the Lorentz force and I dot it with the displacement of my charge. And of course I could sum this over many charges if I wanted. This is written for one charge, but it holds generally. And the dl vector, the displacement, is just the charge's velocity times dt, and so I can factor out that dt and write this as a power, dw dt, the rate of work, which is q e dot v plus q v cross b dot v. And that second term is the magnetic work that's done, and magnetic work has an important property. The important property is it doesn't exist. It's always zero. Magnetic fields themselves never do any work. So how are we going to get magnetic energy out of this? It's kind of a nice surprise. It'll come out naturally. But the only fields that ever do work are electric fields. That's just because the magnetic force is always perpendicular to the displacement of a charge. It can't do work. And I can generalize that to find the power exerted on a charge distribution by turning that Q into a rho d tau and integrating. And I can group together rho v to form my current density J. And so I'm going to have power only when I have E and J that are parallel to each other. So my power is a volume integral of E dot J. So you can think of E dot J as the power density, if you like, the power exerted on a system of charges per unit volume. Okay, so that's cool, but how do we relate that to field energy? So far, this is just computing work done. What we know, though, is Maxwell's equations, and so we can replace E dot J with something that depends only on the fields. The first term here, the first line, comes from Ampere's law. I've solved Ampere's law for J. But Ampere's law isn't all. I also have the Maxwell correction, the displacement current term. And so when I solve for J, remember, displacement current is not real current. It's not made of charges. And so there's no work that's ever done on displacement current. J on the left-hand side here is just the real true current. So when I solve that in terms of the field, I get both a curl of B and a displacement correction. I get a dE dt. And I can start to see how this is going to work, because the E dot dE dt I can write as the time derivative of E squared. So this is the time derivative of the electromagnetic energy, or the electrostatic energy density. So that's something familiar. I like that. The power should be related to the time derivative of the energy density. So that works. What's this other term doing here? Okay, so we can simplify this a little bit, doing a reverse product rule. So setting the stage for integration by parts. That's detailed a little bit in lecture 18. And I just swap the curl around. I get B dot curl E minus the divergence of E cross B. And the left-hand side now, I can replace that curl E with another field without getting my current back by using Faraday's law. So my curl E there becomes minus dB dt, and I have a similar pattern, and guess what? I get the time derivative of the magnetic energy density. So those two terms are giving me both the rate of change of the electric energy and the magnetic energy. Even though only the electric field is ever doing work, the electric field can take energy from either itself or from the magnetic field because of Faraday's law. Then the second term here is a divergence. What is it? Divergence of E cross B. How do we make sense of that? So let's write out what we have. So the rate of work, the power exerted on some charges, is minus the time derivative of the electromagnetic energy density. And so here we've found, at least there's one new term that comes up, but it doesn't look like an energy density very much because there's a divergence. The energy density terms are just the sum of the electric, static, and magnetostatic energy. So there's no extra energy that you get when your field is changing, which is kind of surprising because usually when things are changing, they have kinetic energy. There's no such thing as kinetic energy for fields. There's just energy. So epsilon naught over 2 E squared plus 1 over 2 mu naught B squared doesn't matter if the fields are constant or if they're changing. That's the energy density. But the second term here is a volume integral of a divergence. And if I've taught you anything, you know what we should do. We should use the divergence theorem and turn that into a surface integral. And I'm going to say that that surface integral is of S dot dA. And I've just defined S to be the integrand here, 1 over mu naught E cross B. That has the name of pointing vector. Pointing is spelled funny because it's somebody's name, not the verb to point. So what's this pointing vector? Well, that equation is called Poynting's theorem because Poynting derived it. And it equates the rate of work done on charges in some volume V. Remember that we did this over some arbitrary volume. It doesn't have to be all space. Is minus the rate of change of the field energy. So that's the minus d by dt of the volume integral of U. And that U was, again, the sum of E squared and B squared with appropriate constants. Well, there's another term, which is minus a surface integral. So it's minus a flux. And so it's the rate of energy leaving that volume through the surface. And so now that we're in electrodynamics, we can have the amount of energy in a region change, but we can also have the energy move around. And when it moves, it's represented by the Poynting vector S. And when it moves through a surface, it leaves a region. And it can leave a region without doing work. And so that's why it's subtracted off from this equation. So a little more about the Poynting vector. Its formula is 1 over mu naught E cross B. So you need perpendicular E and B fields to get it. Think of it as an energy current or an energy flux. It's the energy crossing some surface per unit area per unit time. And if you work out the units, you'll get watts per square meter. So it's like an intensity. It's an energy per unit area per unit time, or a power per unit area. There's another special case, which is that if there's no work being done, a lot of times we're talking about electromagnetic fields in vacuum. There are no charges around. If there are no charges around, there's no work done on the charges. And so the dw dt term is 0. We can drop a minus sign and we get du dt plus divergence of S equals 0. We can also get rid of the volume integral because this applies over arbitrary volumes. That equation should look real familiar. It should look exactly like d rho dt plus divergence of J equals 0. That was conservation of charge. And so when there's no work being done on charges, the electromagnetic energy is conserved and it satisfies the continuity equation. The energy density is U, the energy flux is S, or the energy current, if you like. So these are exactly analogous equations. They tell you that the energy can either, the energy has to go somewhere if it changes, right? The exception, the difference is that in the in Poynting's theorem, it's not always equal to zero. If there are charges around, if there are other forces involved, that electromagnetic energy can become a different type of energy. It could become kinetic energy of charges. It could become, heat. It could become other things. But if that's not happening, then we have conservation of electromagnetic energy. So now we can start to see what the other conservation laws are going to look like. They're a little more complicated. Momentum is going to be conserved also, but we have to compute the momentum of the electromagnetic field. And the momentum density, we're going to introduce a new letter for that, which is, since P is already lowercase, we're going to write the momentum density as G. It's a vector. And it turns out that it's proportional to the Poynting vector. So you only have momentum if you have moving energy, which that kind of makes sense in a way. The dimensions are different, and so we have to throw in a mu naught epsilon naught out front. What's the momentum flux going to be? Well, it turns out it's got to be a momentum per unit area per unit time. That has dimensions of force per unit area or pressure, but it's not a scalar and it's not a vector. It's because the analogous to energy, we had a scalar energy density that became a vector energy flux. So when we have a vector momentum density, we end up with a tensor, a rank 2 tensor momentum flux. The tensor here is something that's used in other situations, and so we don't introduce a new name for it. We call it minus Tij, and Tij is called the stress tensor. There's a big old formula for it in lecture 19 that I'll post soon. And the equation is going to look something very similar to Poynting's theorem. It's again the continuity equation in integral form. The rate of change of the momentum of the charges, i.e. the force on the charges, is equal to minus the rate of change of the momentum density. I forgot a d by dt here. D by dt. Minus the rate of change of the momentum density minus the amount of momentum leaving through the boundary. So this is an integral over v. This is an integral over the boundary. And that momentum flux is basically a pressure in the electromagnetic field that's exerted over the surface. So we'll see more about how that works and a formula for Tij in the next lecture notes. But this is the pattern that you should be looking for. It's more and more copies of the continuity equation for different things that are conserved. So you've got a conservation of charge version, you've got a conservation of energy version, that's like the work energy theorem, and you've got a conservation of momentum equation, which is like Newton's second law for fields, if you like, or Newton's third law for fields. All right, that's all.